Hello. Today I bring you a momentary deviation from the general coding content. We'll be doing some simple coding, but the focus is more around electrical engineering this time. Of course, when the two meet for hobbyists, they tend to meet in an Arduino format. Arduinos are these nifty little boards of varying specs that provide a whole bunch of input and output pins that allow you to programmatically engage with hardware. On the simple end, you can turn on and off lights, integrate buttons, integrate with sensors, and do all the stuff that small computers can do like crunch code or do network stuff like emails and APIs if you want. What I'm saying right now is just the tip of the iceberg. I've worked with companies that use Arduinos to monitor server room temperatures and email network admins if there's an undesirable temperature fluctuation. I've seen Arduino's brute force combination locks with a motor. I've myself used one to create a chest that only unlocks if an infrared relay of Alohomora in hexadecimal is broadcasted, and worked with sound modules and accelerometers to create a physical puzzle. These are digital circuits, leveraging microchips to interact with electrical hardware. This is in contrast to traditional circuit design called analog circuits. We begin every endeavor with an idea, as usual, and those ideas generally stem from an unsolicited inspiration. As usual. A few years back, our house got broken into, and that kicked off my physical security and penetration testing obsession. It had been a while since I played with electronics, so I felt it was about time I get a project going around home security. A simple and effective idea that played on my mind was a door sensor alarm thing. Let's define the outcome. We arm the door, and if it opens while it's armed, have an analog reaction, that is, a constantly playing siren to scare invaders and to alert people in and surrounding the house, and a digital reaction to, say, email me in case I'm not home so that I'm aware of the situation. So first things first, I took a trip to my tech store. I was going to buy an Arduino, but the salesperson expertly talked me into buying an ESP32 board with inbuilt Wi-Fi and Bluetooth capabilities and a clock speed that dwarves Arduino's. And while I was there, I picked up a simple magnetic switch and got to work. I tested the general performance of the board and our magnetic switch with a simple breadboarded LED circuit. This worked, but it wasn't a demonstration of a digital circuit, it was actually an analog one, utilizing the 5-volt pins of the ESP32 board. These types of boards generally accept all the same compiled code, so I downloaded Arduino's IDE, and I downloaded the ESP32 serial library, and then I set the serial device to my new board. Now I can upload code to the board and have it interact with components connected to the GPIO pins. I modified our existing circuit to connect the LED and our switch to our 3.3 volt GPIO pins, and I wrote some simple code to perform the same function to validate that the board handles compiled code, and it did. I noticed some funkiness and some flickering during this process, but it's to be expected given how fast the clock speed is. We simply add some minor sleep instructions to the code. This will debounce the current, in addition to stricter toggle flagging in the code, and then the issue was resolved. And this lets us cleanly see when the door is opened or closed. Now would be a good time to preface some things. My approach to this project is very rudimentary, taking into account preferred time constraints and minimal spending, which often meant hacky solutions such as hot gluing over screw mounting and post-apocalyptic PCB soldering over getting a schematic professionally printed with conformal coding overseas, and skipping fancy Autodesk schematic design with Eagle software for a simple but limited browser solution with circuitdiagram.org and pen and paper. These all worked to a satisfying and generally effective degree, but the deeper I go into electronics, the more I would ease away from these practices in future projects. Designing the circuit board layout, be it correct or not, really helped me visualize the circuit and spot circuit errors. The first one looked roughly like this, and it's pretty simple. It was at this point we did a detour from the fundamental goal because one thing was itching in my brain and I needed to get it resolved for my own sanity. I didn't want this thing to require constantly replacing batteries, but I wanted it to remain on in a power outage. So we had to design a miniature 5-volt UPS, and I was dying to figure out how to do it. After a lot of research, I came up with a base design. We had our 5-volt USB power directed into a TP4056 board, which safely would continue the current on while charging an 18650 lithium-ion battery. And when the board detects a cut in the power, the battery would then take over, but the battery only provided about approximately 3 volts. From here, we added a DC voltage step-up module to ensure that the output from the TP4056 stayed around 5 volts, so that the ESP32 board was unharmed. We added a diode to stop the battery from forcing 5 volts back into the USB cable when the power cuts out, and a P-channel MOSFET which acts as a switch to persist our 5 volt stepped up voltage. When the 5 volt output from the USB cuts out, the MOSFET will bridge the battery's power to the board automatically. It's like an electrical toggle switch. Of course, me no big brain engineer. In fact, some would classify me as a lowly mind. So I consulted a friend of mine who was going for his PhD in aerospace engineering, and I gave him the rundown and told him I didn't want to go overkill, but I wanted it to be a generally responsible circuit. We found a middle ground, and although he generally approved, he commented that if I didn't really care about doing it super strictly and I was fine with a subtle bit of power loss, I should probably ground the gate of the MOSFET so no lingering static keeps the track connected in a power outage. In addition to that, I added an indicator LED to help us identify when that change to battery did actually occur, and used another Schottky diode to prevent the current from the primary electricity falsely enabling it. I also added a switch to decouple our UPS from the primary circuit to better isolate our components. Now, I actually had a little siren thing lying around for a while now. I bought it years ago feeling that I'd eventually use it for something like this. There was virtually no documentation that came with it, so I started playing around. So when I tried to power the siren with a AAA 1.5 volt battery, there was not a sound. When I powered it with a 3.3 volt GPIO output pin, there was an annoying, sort of loud wire sound. Okay, cool. Well, how about 4 AAA batteries in series for 6 volts? Jesus, Mary, and Joseph, my eardrums. It was like listening to that egg from the Goblet of Fire. So we can kind of deduce that 5 volts from the board isn't actually that much different. I tested it and we've now found our operating voltage. So I soldered all the UPS parts to their own PCB, and I cut up a USB cable to make a custom power plug to connect it to the board. I tested with the battery, and the power output was about 3.3 volts, which was what we expected from the lithium-ion battery. After I attached the DC stepper, I measured it again with the multimeter and I got about 5 volts output. Huzzah! All the parts work. I tested it with a multimeter, unpowered versus unpowered with a battery versus powered with a battery. I tested those use cases over a long period of time versus a short period of time, just to make sure that we had something stable. And honestly, from a skeptical guy who has fried 2 Arduinos in the past, I was surprisingly delighted to see that it worked without hitch. The UPS board is complete. Now onto our next problem, the siren. If it bled my ears at 3.3 volts, it'd be a walk in the park. We'd just plug it into an I/O pin and call it in code, no dramas. But this wasn't the case. We need the 3.3 volt GPIO pin to trigger the alarm, and a 5 volt power source from the board over another electronic switch would be the way to do that. After a bit of research, I sold myself on the N-channel transistor to be such a catalyst. Now before, we used a P-channel MOSFET, which worked great because it detects when the voltage in the gate is lower than the drain to trigger a bridge of electricity between our battery and the ESP32 board. But this time we need an N-channel MOSFET because it checks when the gate's voltage is higher than the drain for it to trigger the bridge electrically. As in, if the siren was wired from the 5 volt pin to the MOSFET, with the source being technically ground without a full circuit, any voltage in the gate, say 3.3 volts programmatically triggered in our code, is higher than the 0 volts of ground, so it will allow a current. Look, I don't really understand how this works. I tried to, but I'm just a lowly mind. So I moved on. But anyway, we decided in the end to not use a MOSFET and just use a transistor. I don't really know why I made this decision in hindsight, but we're just going to keep going on with it. So here's the updated schematic, and yes, you f***ing nerd, I later realized it was a MOSFET on the design, not a transistor. I'll get to that shortly. So finally back to the code. I wrote some to connect to my local Wi-Fi network, and then I wrote some more code to leverage an existing Gmail account and its app password to send me an email whenever the ARM door is opened. I tested it a bit and left it on while I went to the gym to see if it would falsely trigger, and it all worked fine. I coded this so that when the ARM door trigger occurred, an email would only be sent once, and then the siren would remain on until the device was reset by being powered off. Okay, cool. So now I needed a custom cable to connect the primary circuit with our UPS and our ESP32 board to the magnetic sensor and the siren. I split them like this because I wanted the functional box in an easy to reach place, and the door frame and shape may not work to its size, and additionally I wanted the alarm near the point of entry to frighten intruders the best, and away from the box so that the person disarming it wasn't fighting for their life against the noise. I initially f***ed up on a really hacky and quick calculation. I thought I needed 3 wires, a shared ground, 5 volts for the siren and 3.3 volts for the switch. It wasn't until I built the whole bloody thing and soldered it into a classic PC power cable that I realized I needed an additional ground, or more accurately, a 5 volt negative for the alarm circuit in isolation from the switch, or else it would just always be on by skipping over the transistor logic completely. Another issue that occurred was mixing up the drain and the source of the original MOSFET design that I was earlier explaining, since we switched to a transistor, with the collector and the emitter of the transistor design. I also shorted a female plug somehow that would connect the UPS into the primary operating board, and shit got sizzling. So I updated the schematic to our final design to avoid any confusion in the future. I then made a 3-meter cable this time with 4 wires, and I replaced our shorted female plug. I cannot undersell how exhausting this process was. Updating code on the board to serial log everything that happened and to try and find where the circuit was frying, resoldering somehow connected pins, breaking my fingers setting up a 4-pin mini Molex plug on each of the end of our cables. I got big hands, okay? Anyway, the f***ing Molex plugs just didn't end up having the wires touch each other when connecting, so I just rage quit and cut off all the ends, and for the sake of a lot of potentially waste of time, I directly connected the components together with a 3-meter cable. This is undesirable, but I'd rather move on. I modified our storage boxes with a sanding Dremel and an electric drill. I fitted all of our LEDs and outbound cables. I glued everything tightly into place and secured the boxes with their screws. In the final product, there's some odd voltage oscillation for the siren, which I feel is something to do with our transistor, but it has workarounds like plugging in the siren after the startup of the circuit. This isn't really a thing that happens when we have it directly plugged into the power. It only happens whenever we move to a lithium-ion battery. So in most use cases, I won't even need to do this. But if I ever needed to, this would be as equivalent of a workaround. So I call this project finished, and I will work on now mounting it in my own time, but at least it's going to give you a rudimentary idea as to how to create a door alarm with a bit of pizzazz. Buenos noches, nerds.